Okay, so am I audible? Okay, so hello everyone, I'm Subrata Samanta. So I'm your TA for the thermal physics course that is taken by Professor Demal Banerjee in this semester. So today I will discuss assignment 8 problems. Okay, so in the meantime, if you have any questions, you can ask. Okay, don't hesitate to ask any questions. Okay, so any questions on the weak content on the assignments. Okay, so you can also ask. Okay, so let's share my screen. Okay, I hope my screen is visible now, right? So this is a previous year assignment 8 problems. Okay, so I'll solve these problems. Okay, so hope at the end you will solve this week assignment problems. Okay. So in the first problem, okay, so in the first problems, basically the related to the Carnot engines. Okay, so Carnot engine which low temperature reservoir is at 7 degree centigrade has an efficiency 50%. Okay, so then basically the TL, okay, 7 degree centigrade, that means if you convert to Kelvin, so this becomes 280 Kelvin, right? And this is the low temperature and the efficiency eta is 50%. Okay, so that means 0.5. Okay, so this two data is given and it is desired to increase the efficiency to 70%. Okay, and so this is basically, let's say eta, and eta prime is 70%, so that means 0.7. Okay, by how many degrees should the temperature of the high temperature reservoir be increased? Okay, so you have to calculate TH prime. Okay, for the efficiency when the efficiency 70%. Okay, so the TL is same in this case. So TL is again 7 degrees centigrade. Okay, so the low temperature reservoir. Okay, so this is basically 280 Kelvin. Okay, so how to solve this problem? So first you know that how the Carnot engine operates. Okay, so there is a source, let's say TH, okay, high temperature. Okay, and let's say this is a source. Okay, and you connect an engine. Okay, and there is a sink. Okay, so this is basically at low temperature. Okay, TL, right? And this work done, and this is basically work done W and QH. Okay, it entered to the engine and QL heat leaves. Okay, so the amount of heat leaves QL. Okay, so now the work done W is basically QH minus QL, right? So this is basically Q in and Q out. Okay, so this is basically Q in minus Q out. Okay, and the efficiency eta, the efficiency, so this is work done. So this is work done W, and the efficiency eta is basically W over Q in, right? So here the W is Q in minus Q out over Q in. So this is basically 1 minus Q out over Q in, right? So this is the efficiency of a Carnot engine. Okay, so now because the Carnot engine is a reversible engine, right? So one can show that this QH over QL or Q out, so this is basically Q out over Q in over Q out, Q in over Q out equals to TH over TL. Okay, so which implies that Q in over TH, okay, equals to Q out over TL, right? So now we plug these equations in these equations, okay, in the equations of eta. So the eta is basically 1 minus TL over TH, right? So this is basically Carnot efficiency. Okay, so this is the Carnot efficiency. Okay, so in the given problem, okay, so in the given problem, eta is given. So first step is eta is given. So the case 1, that's a case A. Okay, so the eta is given 50%, so that means 0.5. Okay, when TL is 7 degrees centigrade, so that means 280 Kelvin, right? So you have to calculate first TH then. Okay, so TH, so if you use these equations, okay, so use these equations. So TH basically okay, so yeah, 1 over, so TL over 1 plus eta, right? So this is basically 280 over, so 280 over 1 plus eta, that means 1.5, sorry, 1 plus eta, so eta is 0.5, so TL over TH, so TL over, no, this is basically 1 minus, sorry, 1 minus eta, so this one is basically 0.5. Okay, so this becomes 560 Kelvin. Okay, so that is your for TH. Okay, now the case P, so in a given problem, so there is a two step. Okay, so first step, when the efficiency 50%, you calculate the TH, the values of TH is 560 Kelvin, right? Okay, when the TL is 280 Kelvin. Okay, so this is your 7 degrees centigrade, that means 280 Kelvin. Okay, and the TH is 560 Kelvin, we calculate. So now the second step is, it is desired to increase the efficiency to 70%. Okay, by how many degrees the temperature of the high temperature reservoir increased. Okay, so in the first case, when the efficiency 50%, your high temperature reservoir is at 56 Kelvin, right? But now you have to calculate this high temperature reservoir when the efficiency is 70%, right? So this is basically case B. So in case B, when the eta is 0.7, okay, again that TL is same, 280 Kelvin. We have to calculate, let's say, TH prime, right? So in the eta, let's say eta prime, okay, or eta, so TH prime, right? So in this case, again TH equals to 280, 1 minus 0.7, this is basically 280 over 0.3, right? So which becomes 933.3 Kelvin. Okay, so this is basically TH prime, right? And TH is this 560 Kelvin, right? And your TH prime is 933.3 Kelvin, right? So when the efficiency 70%, okay. So now the questions. So this is basically TH prime is 933.3 Kelvin. Okay, So question, how many degrees should the temperature of the high temperature reservoir be increased? So that means you have to calculate this TH prime minus TH. Okay, so this becomes 933.3 minus 560 Kelvin, so which is equals to, yeah, so which is equals to basically 373.3, right? So 373.3 Kelvin. So initially when the efficiency 50%, okay, you calculate the temperatures of the high temperature reservoir. Okay, so that is 56 Kelvin. Okay, so 506 Kelvin. Okay, now in the case 2, when the so it is desired to increase the efficiency 70%, that means when the efficiency is 70%, okay, you have to calculate again the temperature of the high temperature reservoir. Okay, so this becomes 933.3 Kelvin. Okay, so now how degrees should the temperature increased? Okay, so it's basically difference of these two. Okay, so TH prime minus TH. Okay, so this is basically, so the option is then the option C is correct. Okay, so the option C is the correct. Okay, so far any question? Okay, if not, then I will move to the next one. So the next question is that the 5 kg of water at 0 degree centigrade, okay, is mixed with an equal mass of water at 80 degree centigrade. Okay, calculate the change in entropy. So first of all, there is a mixing of two same water. So this basically, let's say this is one A system and this is system B. Okay, so here is the mass is 5 kg of water, here is also same 5 kg. Okay, and the temperature is T1 and here is T2. So T1 is 0 degree centigrade, so that means 273 Kelvin, and T2 is 80 degree centigrade. So 80 degree means yeah, so this is 80 plus 273, right? So 353 Kelvin. Okay, right. So calculate the change in entropy. So you have to calculate delta S, the change in entropy. Okay, where S is the entropy and delta S change in entropy, and the specific of water may be assumed to be equal to 1 kilocalories per kg times degree centigrade, right? So the specific heat C is 1000 calorie per kg degree centigrade. Okay, so I converted to kilocalorie to calorie. Okay, so 1 kilocalorie means 1000 calorie. Okay, so 1000 calorie per kg degree centigrade. Okay, so that is the specific heat C. Okay, of water is given. Okay, so this is basically between the two temperature 0 degree and this. Okay, and now they are allowed to mix. Okay, so calculate the change in entropy. So how to calculate the change in entropy? So what is the formula for this mixing up to system A and system B? Okay, so here basically your temperature is changes, right? So first you calculate what is the final temperature TF, or the average temperature, right? So first you have to calculate the average temperature, T average. Okay. So what is the average temperature for these two? So in problem 2, so there is a system A and another system, let's say B. Okay. So this one is temperature T1 and this one is temperature at T2. Okay. System A is temperature T1 and system B has temperature T2. Okay. And the specific heat, let's say C1, here is the C2. Okay. Have different specific heat. Okay. Now we allow to mix, okay, of these two systems. Okay. Okay. And let's say this one is the same mass M, this is also M. Okay, mass are same, but the specific heat is different. So then the final temperature is basically C1 T1 plus C2 T2 over C1 plus C2. Okay. So if C1 equals to C, so that means the equal specific heat or the same specific heat, okay, then your final temperature Tf is basically 1 over 2 times T1 plus T2, right? So in this case the change in entropy, so this is the final temperature, the average temperatures. Okay, so this Tf, okay, it's the final temperature. So at Tf is the final temperature. Okay. Right. So now if you see that the mass is the same, so that means the process is isobaric. Okay, so process is isobaric, so we change the entropy. So as the process is isobaric, okay, so that means constant pressure. So isobaric, that means constant pressure. Okay, so the change in entropy, delta S, which is equals to 2m Cp times ln Tf over square root of T1 times T2. Okay, so this is basically a change in entropy, where the Cp is the specific heat at constant pressure because the process is isobaric. Okay, so where Cp is the specific heat at constant pressure. Okay, so in the given problem, so the values of m is given, so m is basically 5 kg, okay, and Cp is given 1000 calorie per, yeah, so 1000 calorie, and yeah, calorie per kg times degree centigrade. Okay, and the T1 is 0 degree centigrade, so 273 Kelvin, and T2 is 353 Kelvin, right, 80 degree centigrade, right? So now the delta S becomes the change in entropy 2 times 5 times 1000 times ln. So your Tf is basically, so you have to calculate first Tf, so this is half times 273 plus 353 Kelvin, so this becomes 313 Kelvin, right? So we plug this value here, so 313 over square root of 273 times 353, right? Yeah, so now use your calculators to calculate this, so please cross check the results. Okay, so this becomes 82.3 calorie per Kelvin. Okay, so in principle it's calorie per degree centigrade, but so let's check the answers. Okay, so the answer is given is calorie per Kelvin, so you choose the unit calorie per Kelvin, because the, so why I am asking that, because here is the given is degree centigrade. So but the answer is given calorie per Kelvin, so you choose that. Okay, so the number is 82.3, so option B is correct. Okay. Okay, so if you have any questions, you can ask, or any doubts. Okay, so far any question? Okay, so if not, then I'll move to the next one. So in the next question, so 3 gram of nitrogen doubles in volume at constant temperatures. So T is constant, okay, and the volume is double. Okay, 3 gram of nitrogen. Calculate the change in entropy given the molecular weight of nitrogen 28. So 28 gram of nitrogen into equals to 1 mole, right? So 1 mole of nitrogen. So first to convert that 3 gram of N2 equals to 3 over 28 mole, right? Okay, and in this case you have to also calculate the change in entropy. Okay, but the volume is double and constant temperatures. Okay. So now how to calculate? So this is basically, if you write down this, so this is, you know that the du is basically your the relation TdS minus PdV, right? So the problem number 3, du, so this is basically the change in internal energy, du is TdS minus PdV, right? So this is basically, and du is equals to CVDT. Okay, so for n mole gas, so this is for 1 mole of gas. So for 1 mole of gas, okay, so for n mole of gas, so now if you write this, so this is basically TdS is PdV plus Cv dt. So ds equals to P over T dV plus Cv dt over T. Now P over T, so if you use ideal gas, so PV equals to RT, right? So this is the ideal gas, okay, where P over T equals to basically R over V, okay. So for 1 mole, okay, so R times dV over V plus Cv times dt over T, right? Okay, so for n mole of gas, so for n mole, okay, let's say for mu mole, okay, for mu mole of gas, your ds, so this is basically nu times R dV over V, right? So for mu mole of gas, basically PV equals to mu RT, okay, right? So this is basically the number of mole, and plus nu Cv dt over T, right? But in the given problem, the temperature is constant. So if temperature is constant, right? So if temperature T is constant, so which implies that dt equals to 0, right? Right. So when the temperature is constant, so dt equals to 0, right? So that means ds, very simple, so only the first terms are there, right? So nu times R dV over V, right? So now in the given problem, okay, we have to calculate the change in entropy when the volume double, okay, so double in volume, okay. So when the volume double, you calculate the change in entropy. So that means, so let's say for volume, so change in entropy delta S, basically nu times R, you have to integrate this. So this is change in volume, okay, S2 minus S1. So in the volume V1 and to V2 dV over V, so this becomes nu times R ln V2 over V1, right? And this delta S is basically S2 minus S1, okay. So that is the change in entropy, okay, delta S, right? So in the given problems, the V2 is basically 2V when the V1 is V, okay, and V2 is 2V, okay. And nu is given, so this is basically 3 gram of nitrogen, so 3 over 28 mole, okay, and R value we know that 8.314, right, joule per mole per Kelvin, right? Okay, so you plug this value, so then the delta is the change in entropy, so change in entropy delta is basically 3 over 28 times R, so 8.314 times ln 2, okay, so 2V over V, so V cancel, so this is basically ln 2. So now what is the values of ln 2? So ln 2 is 0.693, right? This becomes 3 over 28 times 8.314 times 0.693, okay. So now you calculate this, so it becomes 0.617, right? So joule per Kelvin. Okay. Okay, so this is joule per Kelvin. Okay, now you check the answers options. Okay, the 0.617. Okay, so let's check the options. 0.617. So option D is correct. Okay, so joule per Kelvin. Okay, so far any questions? Okay, so it seems that there is no more question, so I will move to the next one. So which law of thermodynamics suggests that there is a tendency for equalizations of temperatures throughout the system? So this is basically zeroth law of thermodynamics, right? So if you look into the zeroth law of thermodynamics, so there will be basically two systems, so system A and system B, right? So if you connect, so let's say have a temperature T1 and the temperature T2, when it's connect, okay, this two systems, so after some times it becomes a common temperature Tf, right? So that is basically zeroth law of thermodynamics. So this is basically zeroth law of thermodynamics. Okay, so then the option A is correct. Okay, so in doubt? এই তোমার অসুবিধা হবে না? তাহলে আমি চেঞ্জ করে দেবো। তোমার অসুবিধা হবে না? Okay, so it seems that there is no more questions, so I'll move to the next one. So the next question is that calculate the increase in entropy when 1 kg of ice at minus 10 degrees centigrade is converted into steam at 100 degrees centigrade, and the specific heat of ice and latent heat of ice and the specific heat of steam and the latent heat of steam is given in the problem. So calculate the change in increase in entropy, right? Okay, so there is a phase change. Okay, so from ice to steam, right? So first the change ice to water, right, and then water to steam, right? So ice converted to water at 0 degree centigrade, right? So at 0 degree centigrade there is a phase change, okay, and the water to steam at 100 degree centigrade, right? So there is a second turning point, okay, and the latent heat of ice at 0 degree centigrade is given, right? So that means you have to calculate the change in entropy. So there is a 4 step. Okay, so first minus 10 degree to 0 degree centigrade, the step 1. So yeah, so this is a problem number 4. So there is a step A where the ice, right, minus 10 degree centigrade to 0 degree centigrade, right, and the step 2, step B, and we calculate the delta S for this process. Okay, and the second is converted to water. Okay, ice to water at 0 degree centigrade. So convert ice to water. So calculate the change in entropy when the ice to water at 0 degree centigrade. So you have to calculate delta S 2. So this is delta S 1 and this one is delta S 2, and the step C is basically the water changes from 0 degree centigrade to 100 degree centigrade, right. So this is basically delta S3. Okay, and step D, so this is basically convert water to steam, okay, at 100 degree centigrade. So convert water to steam at 100 degree centigrade. So this is delta S4, right. So for the first step, okay, so step A. So now I'm going one by one. So in case of step A, so to calculate the change in entropy when the ice is changing minus 10 degree centigrade to 0 degree centigrade. Okay, so what is the formula for this? So delta is 1. So this is basically so in the previously we used formula, right. So mass times the specific heat, okay, times the logarithm of ratio of the temperature, right. So that means delta S1 is basically mass times the specific heat of ice, because the ice changing minus 10 to 0, right. So we have to use the specific heat of ice, so C ice, okay, times the logarithm of the ratio of the temperatures, right. So T0 and T minus 10, right. So T minus 10 basically the temperatures minus 10 degree centigrade. Okay, so you have to convert it to Kelvin. So T minus 10 is basically 273 minus 10, so it's 263 Kelvin, and T naught is 273 Kelvin. Okay, and I know what is the C ice. Okay, so C ice is given in the problem, the specific heat of ice. So what is the specific heat of ice? So the specific heat of ice is given in the problem. So it's basically, yes, so the specific heat of ice is 0.5 kilocalorie per kg degree centigrade. Okay, so 0.5 kilocalorie per kg time degree centigrade. Okay, so this is the step A process. Okay, so ice converted minus 10 degree centigrade to 0 degree centigrade. Okay, and so due to this change, the change in entropy is basically m times C ice times ln T naught over T minus 10. Okay, so m is basically 1, so 1 times and 0.5, so I convert it into kilojoule. Okay, so 1 calorie equals to 4.2 joule. Okay, so 1 kilocalorie equals to 4.2 kilojoule, right. So that means the specific heat of ice I converted to 0.5 times 4.2, okay, times, so where m is basically 1 kg, okay, 1 kg of ice, okay, times logarithm of T naught is basically 273 0 degree, and T minus 10 is minus 10 degrees centigrade, so it's converted to Kelvin is 263, right? So this becomes, so if you calculate this, okay, so this is basically your unit is kilojoule, right, per Kelvin, okay, so kg is cancelled, okay, so this one is a kg, so m is 1 kg, so this kg cancels, okay, and by conventions I wrote in Kelvin, okay. So now for the second case, okay, step 2, so step B, so the first case is complete, okay, we calculate delta S1, so this is your delta S1, okay. So in the second case is that the convert ice to water at 0 degree centigrade, okay. So what is the change in entropy due to the conversions of ice to water at 0 degree centigrade? So that's required a specific latent heat, right? So delta S2, so this is basically the mass times the latent heat, okay, of ice, right, because ice changing to water, okay, at 0 degree centigrade, so temperature T 0, right. So this is your latent heat, so Li is the latent heat of ice, okay, at 0 degree centigrade, okay, and that is given in the problem, okay. So latent heat of ice, so this is 3.4 times 10 to the power 5 joule per kg, so I converted to kilojoule, right. So 3.4 times 10 to the power 5 joule per kg, so if I convert it to kilojoule, so this is basically 3.4 times 10 to the power 2 kilojoule per kg, okay. And we know T naught is basically 0 degree centigrade, so 273 Kelvin, and m is 1 kg, so 1 times 3.4 times 10 to the power 2, right, and this basically 273, and the unit is, so kilojoule, and this one is kg, okay, and this one is kilojoule per kg, this one is Kelvin, so kilojoule per Kelvin, because the delta S1 I calculate in units of kilojoule per Kelvin, okay. So this is also in kilojoule per Kelvin. So now I am going to the step 3. So step C, okay, yeah, so far any question? So this one is also calculated. So in step C, we have to calculate the change in entropy when the water, it changes 0 degree centigrade to 100 degree centigrade, okay. So again the same procedures as in the step A, okay. So when the ice changing minus 10 degree centigrade to 0 degree centigrade, right, so use the same formula. So then the, in case of step C, so delta is 3, this is basically same, this is mass times, in this case the specific heat of water, right, not ice, so specific heat of water times ln is temperature is basically T final, so whatever final temperature is 100, and the initial temperature T naught, okay, and this is ln, okay, log. So again this is a 1 kg, so 1 times what is the specific heat of water, okay, so is also given in the problem. So yeah, so basically 1, the specific heat of water may be 1 kilocalorie, let me check, yeah, so 1 kilocalorie per kg times degree centigrade, so So this is basically 1 times, so C water is 1 kilocalorie per kg time degree centigrade, but I converted to kilocalorie to kilojoule. Okay, so this is basically 4.2 kilojoule per kg time degree centigrade. Okay, so this is basically 1 times 4.2 time ln, so 100 degree means that if we convert it to Kelvin, so 373 Kelvin, right, over 273, right, 0 degree, right, and the unit is basically kg over Kelvin, right, sorry, kilojoule over Kelvin. Okay. So now the step 4, okay, the last one, step D. Okay, so in this case, so sorry, yeah, so the step 3 is calculated. Okay, now in the last step is basically convert water to steam. Okay, so what is the change in entropy when if you convert water to steam at 100 degrees centigrade? Okay, so that is delta S4. So delta S4 is exactly same when the ice changing to water, okay, at 0 degrees centigrade, right? So basically mass time latent heat over the temperature. So this is the same formula. So mass times latent heat of water, okay, over, yeah, so the latent heat of steam, not water, steam, okay, and here is basically latent heat of water. So ice, basically when the ice change to you can say that the latent heat of, just a minute, yeah, so the latent heat of ice, so this one is fine, yeah, this one is fine. So and in this case the latent heat of steam, okay, so m times the latent heat of steam over the temperature T100. Okay, so this is basically again 1 kg of ice converted to 1 kg of water converted to steam. So what is the latent heat of steam is basically given in the problem. So 22.68 times 10 to the power 2. So I converted to kilojoule, right? So that's why. So kilojoule, okay, per Kelvin. So this is basically 373 Kelvin. Okay, so the unit is kilojoule per Kelvin. Okay, so now the total change in entropy for the entire process, okay, ice, so the process is basically ice at minus 10 degrees centigrade, okay, to steam at 100 degrees centigrade. Okay, so that this process, okay, so the total in the change in entropy for the entire process is delta S, is basically delta S1, delta S2, delta S3, because entropy is additive property, right? So to add the entropy for the 4 individual processes. Okay, so once you add this, okay, so this basically, so I'm writing basically 4.2 times 0.5 times ln 273 over 263 plus 3.4 times 10 to the power 2 over 273 plus delta S3. So delta S3 basically again 4.2 times 1, right, times ln 373 over 273 plus again the latent heat. Okay, so the entropy change due to latent heat. So this is basically 22.68 times 10 to the power 2 over 373. Okay, so the all are in the same unit. So this is basically kilojoule per Kelvin. So now if we use your calculator, okay, to calculate this thing, so this becomes, okay, so please cross check the answers. So 8.714 kilojoule per Kelvin. Okay, yeah, so far any question or any doubts if you do not understand? Okay, so this is basically your total change in entropy. So total change in entropy. Okay, so now let's check the options. Okay, 8.714, so 8.714, so option C is correct, right? Okay, so this is basically four process. So calculate the increase in entropy when 1 kg of ice minus 10 degrees centigrade is converted into a steam at 100 degrees centigrade. So this is done in the four process. First convert ice to water at 0 degrees centigrade, okay, and then water to steam at 100 degrees centigrade. So that's why you have to calculate the change in entropy due to this full process, okay, and add up, okay, at the end. Okay, okay, so any question? Okay, so if there is no more questions, so then I will move to the next one. So the next question is basically during the melting of a slab of ice at 273 Kelvin, okay, at atmospheric pressure, okay, so positive work is done by the ice water system. Internal energy of ice water system remains constant. Internal energy of ice water system increases and internal energy of ice water system decreases. Okay, so how do I know? So this is basically the melting of slab of ice, okay, at 273 kelvins, right? So this is fine because ice is changes pH at 0 degree centigrade, right? So first of all, so change in internal energy basically du, right? So the first law of thermodynamics tells you that the du is basically dq plus dw, right? So I put a cut here because these are the inexact differentials, okay, and du is exact differentials, okay. So that's why. So now, so here is the process is basically the melting of a slab of ice at 273 Kelvin. Okay. So that means dq is positive or negative. So dq in this case positives because the system absorb heat from the surrounding, right? That's why there is a melting of slab of ice. So dq is positives at the greater than 0. Is a positives because because the system absorb heat from the surrounding. So system absorb heat from surrounding. Okay. Yes. sorry, can you repeat this? 2 point log base 10 x over y. Yes, x by y is, yeah, so log 10, if you convert it to ln, so basically 2.30 and log 10, so this is basically e, right? So what is the values of e? You know the values of e. The values of e is basically 2.303, right? So this log ln is basically log at base e x over y. Okay, right? So now to convert this base e to 10, right? Because left hand side you have a 10, right? So this is basically log, no, I think the values of e or the values of 1 by e, which one is 2.303? So log, so I can write this basically log 10 and I think this one is 3.303, so 1 over e basically, just a minute. So your the values of e is not 2.303, the values of e is basically 2.71. So then you have to, I will say that this 2.303 log 10. So we converted this, right? So first you have to convert a log 10 x over y to log e x over y. Okay, how do I convert this to? I remember the log property. Yes, so how to convert this? Because log a, let's say base h x, okay, and if this is x, then it's 1, right? So yeah, how do you convert this? So you can convert in this way. Let's say log 10, okay, let's say x over y is equals to log e x over y over log e 10, right? Okay, so now what is the values of log e 10? the values of log E10 2.303, right? Yeah, so that is basically, then it's log EX, 10 times log 10 x over y equals to log E x over y, right? So if it is, so this is basically 2.303. Yeah, then it's fine. So this implies that 2.303 times log 10 equals to log E. Okay, so that means this is correct. So this is the property of log. If we use these properties of this property, so the log 10 x over y basically log E x over y over log E10. Okay, you can put any number here. Okay, so log, let's say z x over y divided by log z a 10. Okay, so I choose z equals to E. Okay, because I want log E x over y. Okay, it's clear. Okay, so then I'll come back to this problem. Okay, so this is basically the melting of a slab of ice at 273 Kelvin. Okay, and at atmospheric pressure. Okay, so in this case, because the melting of ice, okay, so this is basically the system absorb heat from the surrounding. Okay, that's why it's melting. Okay, so the dq is positive in that case. Okay, so now the second one. Okay, so dw. Okay, so it is positive or not, or negative. Okay, so dw is basically work done, right? So you can write this dw is basically minus pdv, right? So now, so at constant pressure, so atmospheric pressure, that means pressure is constant, so P is constant. So dV is positive or negative when the melting of ice. Okay, during the ice, so during the melting of ice, okay, the change in volume positive or negative. Okay, so volume increases or decreases. Let's say you have a slab of ice. Okay, now it's melting. Okay, it start to melting. Okay, so its volume is decreases or increases as compared to the phase when this becomes ice. Okay. So during the melting of ice, the volume is decreases, right? Volume is decreases. Why this is happening? Why the volume is decreases? Okay, so this is basically, so during the melting of ice, so during the melting of ice, the volume decreases, that because the density of ice is less than the density of water, right? So during the melting of ice, volume decreases. Okay, this is because the density of ice, okay, is less than the density of water, right? Because ice converted to water, right? Okay, so that the volume will decrease. Okay. So if the volume decreases, then dV is negative, right? Okay, because dV basically the V1 minus V2. So if V2 less than V1, then dV is negative. Okay, so then dV negative, that means dW is basically minus P dV, that is positive, right? So it's positive. Okay. And we already know that the dq is positive. Okay, so this implies that du is dq plus dw. Okay, so I choose the conventions here that the dq plus dw. Okay, where I put the dw equals to minus pd, but in some books, okay, you can see that these are dq minus dw, but dw is plus pd. Okay, so both same. Okay, and both are same. Okay, so I choose these conventions. Okay, so that's why I put the plus sign here. Okay, and the minus sign there. So that means, so du is becomes positive, right, since both dq and dw are positive. Right? So the change in internal energy is positive, that means the internal energy increases, right? So let's check the options. Okay, yeah, so the internal energy of ice water system increases. Okay, so that means the option C is correct. Okay, yeah, so far any question? Yes. Yeah, so work done is positives or negatives. So in these conventions, when the system works on the surrounding, right, then dw is positive. But when the I think system is worked on by the surrounding. Okay, so basically systems works on the surrounding or system works by the surrounding. Okay, so if it is on the surrounding, right, then it's positive. If by the surrounding, then it's negative, because the volume is decreases if system works by the surrounding, right? So let's say we have considered a piston. Okay, and we compress this. Okay, so your initial, let's say, volume is v1. So when you compress it, that means by the surroundings. Okay, so this is your system, right? So this is your system. Okay, and if you put a work done on this, okay, so and the final state, let's say this. Okay, this is basically our volume v2. So your change in volume then negative, right? So you work on the system, right? So a system basically inside the piston. Okay, and you compress it, so that means the volume it changes v1 to v2, but the dv is negative. Okay, because the volume is decreases. Okay, when it's worked on by the system. So in this case, dw is basically minus p dv, so that is positive. Okay, but suppose you consider a reverse situation, so opposite scenario. So when the system works, okay, so that means, so this is your v1. Okay, so after some time, okay, so let's say this one. Okay, the system works. Okay, so that means this is v2. Okay, so in this case, your dw is according to these conventions minus p dv. So this dv is positive because dv in this case positive, right? So then dw is negative, right? So compare these two scenarios. So it's understood, or is there any confusion? Okay. But in some book, if you look into there are some books, so they use here minus sign, right? So in this case, the dw is negative positive it changes. Okay, so the convention is important. But if you look into the physics concept, so this is basically if you draw a pistons, okay, and study this, so this is basically when the work done by the surroundings, okay, so then you see that the volume it changes, okay, so then the dw is positives or negative. But when it's I think expand, okay, so that means the system work, okay, on the surrounding, okay, so then the dv is positives, okay, so then the according to this conventions, okay, dw is negative. But if you use the another conventions, okay, so where it's basically dq, sorry, du is basically dq minus dw, okay, so where dw is basically pdv, okay, you can also use these conventions, okay, right. So I put here the minus sign, okay, that's why I'm not using the minus sign here, okay. But that is basically difference in the conventions, okay, but the physics is same, okay, for both the cases. Okay, so now I'm going to the, so now I move to the next one, so the problem number 7. So it's basically a refrigerator is working between the temperatures of melting ice, okay, and that of outside atmospheric temperature 70 degrees centigrade. So melting ice means that 0 degrees centigrade, right? So this one is 0 degrees centigrade, another one is 70 degrees centigrade, right? And this is a refrigerator, okay? It's not a Carnot engine, okay? This is basically the reverse of the Carnot engine, okay? And calculate the calculate the energy required to freeze 1 kg of water at 0 degrees centigrade, okay, given the latent heat of melting is this, okay. So how the refrigerator works, okay, so it's basically the opposite, okay. So if you put the work on the into the system, right, so it's basically there is a high temperature bath and there is a low temperature bath, okay. So this is high temperature, okay, and this is low temperature bath, okay. And if you put work done on the systems, okay, then it converts from low temperature to high temperature. So that is the how the refrigerator works, okay. So this is your engine, okay, refrigerator, R, right. So this is, let's say, QL and this is QH, okay, right. So now how much energy is required in this process? So what is your TH? So TH is basically, yeah, so the outside atmospheric temperature, that means the high temperature, so this is 70 degrees centigrade. So TH is 17 degrees centigrade, so which is equals to 290 Kelvin, okay. And your TL is basically the low temperatures one, so 0 degrees centigrade, right. So it's 273 Kelvin, right. And calculate the energy required to freeze 1 kg of water, okay. So then this is basically your work done, okay. So the energy required means that this W, okay, so the energy required, okay, so TH is 290 Kelvin and TL is 273 Kelvin, okay. And the energy required to convert this, so this is basically W, okay. So this is basically 1 kg times your latent heat, okay, L time, so L times then the change in temperature, right? So this is basically T1 minus T2, right? So basically, yeah, so TH minus TL and over TL, right? So this L is the latent heat of so latent heat Q is given, right? So latent heat of melting is given, so 334 joule per gram, so if we convert it to kg, so converted into kg, so 1 kg of water at 0 degree centigrade, right? So that means TL, so 0 degree centigrade, so if you calculate the energy required to freezing this, so this is basically W, so it's latent heat 334 times 10 to the power 3 joule per kg, right? Yes, so joule per kg, yes, and then this becomes TH minus TL over TL, so TL at the 0 degree centigrade, so 273 Kelvin, right? So plug this value, so 1 kg, so this one is a kg, so 1 kg times 334 times 10 to the power 3, then joule per kg, so it's cancelled, times TH minus TL, so 293, sorry 290 minus 273 over 273, this is basically joule, okay? So Kelvin cancel, okay, so this one is also Kelvin, this is also Kelvin, so 334, then this is basically 334 times 17 over 273 kilojoule, right? So this becomes 20.8 kilojoule, okay? This much energy required, okay, to convert 1 kg of water into ice, okay? So it's 20.8 kilojoule, okay? So let's check the options. Yeah, so the options B is correct, okay? Yeah, any question or doubts if you have? So remember that the refrigerator is basically working in the reverse of the Carnot engine, okay? And the efficiency also the inverse of the Carnot engine. So here you have to put the work done, okay? So this is the example where the work done on the systems, okay, not by the systems. So the Carnot engine basically work done by the system, by the engine, but here you have to put the energy, okay, on the system, so to convert the heat from the low temperature to high temperature. So that is the way the refrigerator works, okay? Okay, so it seems that there is no more questions, so I will move to the next one. So a Carnot cycle, so the operating between the two temperatures. So here is the Carnot cycle, okay? It's operating between the temperatures 1400 and 30, okay? So first we convert it to your TA is the high temperatures, okay? 1 H 1400 plus 273, so this is basically 1673 Kelvin, okay? And the low temperature one is 30 degrees centigrade, so it's 303 Kelvin, okay? So calculate the work obtained from the engine. So from the engine you work obtained, right? In the previous case the energy required to the engine, okay? But in this case you have to calculate work obtained from the engine. So this is because this is the Carnot cycle. Okay. So now how to calculate the work done? So in the Carnot cycle, so if you draw a Carnot cycle, so the schematic diagram is basically, so TH, the high temperature one. Okay, so this 1673 Kelvin. Okay, and there is a engine, and there is a low temperature bath. Okay, so TL, this becomes 303 Kelvin, and this is the work done, and this is QH and the QL. Okay, so the work done W is basically QH minus QL, right? But you know TH, TL. So TH you know 1673 and TL you know 303. So how to calculate QH, QL? Okay, and you also know maybe QL. Let's say, yeah. So the receive a heat 4.2 kilojoule. So a Carnot cycle operating between these two temperatures that receive a heat 4.2 kilojoule. Okay. So that means, so receive heat means that, so this is your engine, okay, and receive heat, that means QH. Okay, so the QH amount of heat received by the engines. Okay, okay, and it leaves QL amounts of heat, right? So that means QH is 4.2 kilojoule, right? So you have to calculate first QL. So once you know the QL, you just differentiate these two numbers. Okay, to calculate the work done. Okay, obtained from the engine. Okay, so this is the work done from the engine. This is work done from the engine. Okay, so now this is the Carnot cycle. So this is a reversible cycle. Okay, right. So by using the properties of that, so there is a two isotherms and two adiabatics. So by using this, so it is easy to prove that the QH over QL is becomes TH over TL. Okay, so that means the QL is equals to TL over TH times QH, right? So what is the TL? So TL is the low temperature bath temperatures 303, the high temperature bath is 1673 times your QH is given, so 4.2 kilojoule. So that means this becomes 0.76 kilojoule. Sorry, right? So 0.76 kilojoule. So once you know this, so the next one is the very simple. So you just calculate the difference between this. So QH minus QL. So QH is basically 4.2 minus 0.76 is kilojoule. Okay. So this is basically 3.44 kilojoule. Yeah. So any questions? I think these relations it is easy to prove. Okay, so you have to use this two adiabatic and two isotherms. So this one basically the isotherms, adiabatic, again isotherm, okay, and adiabatics. This is reversible cycles. Okay, so by using these four properties, okay, you can derive this. So where the temperature is basically, this is the isotherms, the TH, and this is also isotherm, is a constant temperature TL. Okay, and the heat entered through this process QH. Sorry, in this process adiabatic process, so no change in heat. So this process, so QH and it leaves QL. Okay, so this is the PV plane. So it is easy to show that the QH over QL basically TH over TL. Okay. So using these relations, so you calculate QL, okay, because the TL, TH and QH are all given. Okay, so once you calculate QL, so now you take the difference. Okay, and that's the answer. Yeah, any question? Okay, so if not, then I'll move to the next one. Okay, how many problems are left? 2, 9 and 10. Okay, so in the next problem, so Carnot cycle is operating between source of temperature T1 and sink T2. So again, I think if you draw a cycle, so this is your source temperatures, so T1, and this is your sink, so it's temperature T2, and the engine is basically this. The engine operate in between. Okay. So this is QH and this one is QL, right? So what is the most effective way of increasing the efficiency of the engine? Okay, so what is the efficiency of the Carnot engine? It's basically eta, right? So the efficiency of the Carnot engine is basically W, the work done, over Q in. So this is basically QH, right? So this is Q in and this is Q out, right? So W over Q in, that means QH. Okay, so this is your efficiency, right? And W is basically QH minus QL over QH. So its efficiency then 1 minus QL over QH, right? And this is also equals to 1 minus TL over TH. Again we use the same equality, that QH over QL equals to TH over TL. Okay, so 1 minus TL over TH. Now if we increase the efficiency, okay, so there is a two way to increase the efficiency of the Carnot engine. Okay, what are the two ways? So from this equation, okay, so this is basically so let's go into the details. Okay, so the efficiency of the Carnot engine, efficiency of a Carnot engine, this is eta, basically 1 minus TL over TH. Right? So since this is 1 minus some quantities, right? So how to increase the efficiency? So basically increase, so the first step is that increase, so eta, let's see this way, so eta increase, that means TL minus TH decrease. So if we increase the values of eta, so that means we have to decrease the values of TL over TH, right? Because if we decrease the values of this ratio, that means 1 minus this basically increases. right? So now there are two ways we can do this. So one way, how to decrease the ratio TL over TH. So one of the ways is that the TL decreases, another way TH increases. Right? Because if we increase TH, okay, that means this is the TH in the denominator, so it decreases, right? So the ratio is decreases. And if we decrease TH, so TL is the numerator, so it also decreases. So there are two ways. But now the question is that which one is the more efficient or the more effective way we can do, okay, among these two processes. Okay, which one most effective? Okay, so which one is most effective? So how do I know? Any hint? Okay, so let's consider the scenario. So case A, okay, so this is basically case 1, okay, where you decrease the TL, right? So that means in this case your TL becomes TL minus delta T, right? But the delta T is positive, so delta T is positive, okay, and also TH is greater than TL. Okay, the high temperature this one is a low temperature. So now if you decrease the temperature, that means TL to TL minus delta T. So in this case, let's say the efficiency is eta 1. So eta 1, so what is the values of eta 1 then? 1 minus TL minus delta T over TH, right? Okay, so this is, let's say, equation number 1. And case 2, so TH is TH plus delta T, right? So increase the high temperatures, right? High temperature, increase the temperatures of the high temperature bath. Okay, so TH plus delta T, where the delta T is positive, right? So in this case, the efficiency is eta 2 is 1 minus TL over TH plus delta T, right? So now your job is to differentiate these two. Okay, so the equation 1 minus equation 2. So basically eta 1 minus eta 2, right? So this becomes, so 1 is cancelled, so minus TL over TH plus delta T, right? That's 1 minus this, and minus 1 plus TL, sorry, eta 1 is TL minus delta T, this one is TH, okay, and this one is TL over TH plus delta T, right? So this 1 is cancelled, so now is basically doing the simplified algebra. So TH times TH plus delta T, if you multiply with this, so TH plus delta T times minus TL minus delta T, right, plus TL TH. Okay, since delta T is small, so basically, so let's expand this. Okay, so TH plus delta T, and this one is minus TH TL plus delta T TH minus delta T TL plus delta T square, right. So again there is also plus TL TH. So now this TL TH and this TL TH cancel. Okay, so this becomes TH minus TL times delta T plus delta T square over TH plus delta T, right. So this is positive or negative? Because delta T square is positive, right. So this is the positive number, this is also positive, right, because delta T positive, and TH minus TL is also positive because TH greater than TL, so TH minus TL is positive. So that means this product is also positive. Okay, so the full quantity is positive, right. So that means eta 1 is greater than eta 2, right. So what is the process of eta 1? This one, right. So case 1, so that means the lowering the sink temperature, right. So this one, so TL, if the TL decreases, so thus lowering of the sink temperature right. So sink basically this TL, okay. So this is the sink temperature, so this is your source, okay. So this is source, this is sink, okay. So lowering the sink temperature is the most effective way, to increase the efficiency of the Carnot, to increase the efficiency of the Carnot engine. Okay, any question? Yes. Okay. Yes. Hmm. Yes, at temperature 20 degrees Celsius is converted to ice. Yes. Yes. Is any other information is given? So this is basically same problem. So if you look into this problem, so okay, so I read this question again, repeat this question again. So calculate the increase in entropy or the change in entropy, right? So when 1 kg of ice at minus 10 degrees centigrade is converted into a steam of at 100 degrees centigrade, right? Yes. Is it, so if we first calculate the delta S, it's change in entropy. Yes. So now if are basically okay, so you're questioning about the sign in the problem, right? Delta is positive or negative. So in this case, so if we calculate the entropy, so I do this basically there are 4 ways. So you know that the m and the specific heat times the logarithm of the ratio of the temperatures, right? And then during the phase changes, if we use the latent heat. Now the question is that so your question is basically the sign of this delta is, right, is positive or negative, that you want to ask, right? Yes, I mean so initially your entropy is fine. So yeah, so when the entropy is positive, I mean it's an entire process. Okay, so okay, so let's see that. So basically, so delta S total is always positive, right? That is basically your second law of thermodynamics, right? So change in entropy always positives. Okay, in the total system, that means the system plus surroundings, right? Right. So now in your systems basically changes water to ice. Okay, so that is basically system, it changes water to ice. Okay. But there is no change in surroundings. Yes, that constant pressure, right? Yeah, so at constant pressure, so that means entropy change is basically delta S is m Cp and this ln T2 over T1. Okay. And this is a positive number, right? Because in this case the entropy is always positive. So because in the surrounding there is a no change in entropy. Okay, so and delta S total is positive, so it's positive. Okay, so let me think again. I mean, if we says that hmm, so in the first process, so this is basically log x over y equals to minus log x or y over x. That is the case. Basically, if I change in the forward way, so that means ice to water. Okay. Yeah, so basically you're changing the temp T1 and T2 value as well, right? So in this case, what is the values of T2? So use the T2 basically your okay, so the convention is basically here. Okay, so ln x over y is basically minus ln y over x, right? So now if we use always that the T1 is your the initial process and T2 is your final process. Okay, so that means when we change ice to water, right? So in this case, you are changing entropy delta is basically m Cp, okay, or C, let's say ice to ice. Okay, so C minus 10 degree centigrade to ice 0 degree centigrade, right? Okay, or you do opposite way. So this is the first step, and let's say, okay, so in your problems, let's go back to yeah. So basically your problem is that 10 gram of water at 20 degrees centigrade to ice at minus 10 degrees centigrade. Okay, so how many processes are there? So first you change water, so 20 degrees centigrade to sorry 20 degrees centigrade water to 0 degree water, right? So in this case there is no change in sign, okay, because in this case you have to use the notation is that delta S is mc ln T0 over T20. Okay, if you use the other one, so basically minus mc ln T20 over T0, right? Yes. Then you change the phase, 0 degree ice, right, and then 0 degree ice to minus 10 degrees Celsius, right? So that is again the same, use the same formula, but in the mid step we have to use delta is basically m times latent heat over T naught, right? So in this case there is no change in temperature, right? So that means there is no sign, but in this case the sign is basically how to use this T naught and T20, right? T20, right? So if we write in this way that T20 over T naught, then there is a minus sign, or if you write that, okay, so I changed 20 to 0, so T0 in the numerator and T20 is the denominator, right? But if you do a reverse process, okay, so 0 degree to 20 degrees centigrade, then you have to use this one, right? It's clear or not? I mean, so let's say so this is your 20 degree to 0 degree water, right? Now if you change that, so 0 degree centigrade to 20 degree centigrade water. So in this case your delta S is basically mc times ln T20 over T naught, right? Final over initial, right? And that is exactly because minus delta S this process, okay. So let's say this one is 1 2, so minus delta is 1, right? So the minus sign is basically, I mean, absorbed in this convention. Okay, so you always write that the final one is the numerator and the initial one is the denominator, right? So that's convention is, I mean, take care of the minus sign. So, and in this case there is no change in sign because this is basically at 0 degree centigrade, right? It changes the phase, that's why. It's only required the latent heat. And the again the other one, the third step is again the same procedure, right? So you, when you change 0 degree to minus 10, so T minus 10 over T0, right? Or when changing minus 10 to 0, right? So then it's basically ln T naught over T minus 10, right? So same way. Okay, so Yeah, so I mean you are right. So this is basically there is just a minus sign, but this minus sign is basically take care of this. Okay, so how to use your T20 and T10, okay, T naught. This. Okay, all right. So yeah, so there is a one more questions left. I mean you know this one. So the criteria process to be reversible is that must be. So you know when the process is reversible. So there is a I mean the process is reversible, that means it's basically the quasi statically, right? So you have to move the system very slowly, okay, such that, so what do you mean is a quasi static? So this is option C correct, and all option B is also correct, so that means option D correct, okay, so both B and C. So what do you mean is a quasi static? So quasi static basically, so each equilibrium state, so when you change from one state to another, so equilibrium does not equilibrium maintain, okay, so equilibrium should be maintained, okay. So each equilibrium state differing from the previous one differing from the previous one, okay, by infinitesimal change in the system parameters, by an infinitesimal change of the system parameter, infinitesimal change of the system parameters. So what does this mean? That means if you draw a, let's say, the reversible process, that means the Carnot engine, let's say this, right? So this is PV plane. Let's say I consider this point, okay, and again so this point, let's say I know this is basically P1, P1, T1, and this point is P2, P2, T2. So once you change this, so this is an one equilibrium state, this one is another equilibrium state, right? For the pressure, temperature, volume P2, P2, T2. Okay, so each equilibrium state, okay, differ from the previous one. Let's say this P2, V2, T2 is differ from the P1, V1, T1. Okay, by an infinitesimal change of the parameters, sorry, very slowly change. Okay, where the difference delta P is basically P2 minus P1 is tends to 0. Okay, very close to 0. Okay, and similarly for delta T, delta V. So we change slowly, okay, such that your delta P tends to 0, delta T tends to 0, delta V tends to 0, and that is basically the quasi-static process. Okay, so this process is called the quasi-static process. Okay, so in this way, both isothermal expansion, so this is basically expansions, okay, and this is the compressions, okay, both are reversible. So then this is the process reversible, and there is a no dissipative, okay, not non-dissipative as well, right? Okay, so then the option D is correct. Okay. Okay, so far any question? Okay, so it seems that there is no more questions, so then I will stop the session here. Okay, so see you on the next Sunday at 4 p.m.